Okay, my wonderful friends, Roger once again. We're going to do something here, looking at something today that my friend Pierre sent me about a guy who says he discovered an old rare dinosaur era fossil bone encapsulated in stone. See, he sees these little ridges and he's saying, ooh, there's a bone in there. And he's right, there is. But what it's encapsulated is just not rock. That was the flesh that it was in. I am going to show you examples of it right now. I have them in every different, I can show you pretty good proof of what I'm talking about. What he ended up doing is chiseling all of this stuff off, which was literally the flesh and muscle and tissue and tendon, and getting down to what he considered to be the bone, which it is. And it's a different, you see this is the bone here? The rest of this is biological. I'm going to show you that. This is a goose's head. I've shown this a million times. Everybody's starting to think it's my pet. He's my best friend now. There's just feathers up there. And this turns, they turn into basalt, they turn into granite. But you can find the anatomical structures inside if you do things very carefully. And he's right. But what he's chipping away is the flesh. This is a bone. And this thing actually bleeds. When they take them out, you take them out of the ground, this actually bled. And I can show you that it bled. And I can show you the red blood that came out of here. And I can show you that it actually creates its own clotting factor, exactly what happens in the body. It's called fibrin. Anyway, we're going to go over, and you can actually get meat. They look just like meat when you take them out of the ground. See, you throw that on the grill. Not quite enough for an actual meal, but anyway, we could do some research on this. And concretions are not just an accumulation of goop around a bone. That's all they can think about is bones. It's not just bones, it's everything. Everything transitions because of transition elements. When you die, all of this stuff on the sides here, it becomes unstable. And these guys move in a wet, aqueous conditions, and they take over. It's called nucleophilic substitution. That's why this is no longer flesh and bone. This is basalt or some form of stone. They call it all kinds of different things, igneous and metamorphic and all kinds of nonsense. They're body parts that have transitioned into mineralized, solid flesh and bones and tendons. And they're all different. And I could show you, this is the bone ball on one side. The other side still has the muscle on it. He would take the muscle on to get down to the bone. And I can show you the capsule of the bone, the marrow. We're going to look at everything. So let's get started. Okay, this is a head that was petrified in the same manner as the mud fossils. And nobody carves a head and leaves the nose with the cartilage exposed and pushes off the flesh to the side and makes a carving like that. This is blood. Blood is iron oxide. Scott Walter saw this, and Jim Burchell and Arlie Caudle. This goes back 6-7 years. They took this down to Scott Walter to have him show this on TV. He opened it up and in 20 seconds, nope, I'm absolutely certain it's just a carved head, there's nothing here. Well, that was 6-7 years ago. We could have been, that ruined everything for us. And he's never turned around. I went back and forth with him over and over, and he finally just said, look, I'm the expert, and get lost, and that was the end of it. Scott, you should relook at this. Scott Walter from the History Channel. All right, 20 seconds to destroy the credibility of all the work we did. Okay, I want to give credit to this guy because he's not a fool. He's doing the reverse of nucleophilic substitution. He's doing chemistry to change and be able to extract these different fleshy and tendon parts, and he's using chemistry. He's doing a pretty good job. He thinks it's encased in a rock. Well, it's not a rock. So I'm going to just cut to the chase on every spot he does that. Okay, my friends, this is going to be fun. This is from my friend Pierre Brunet up in Canada. Thank you, Pierre. Daily Mail video, shocking videos, puts this up here about this guy finding a dinosaur bone. And he's going to uncover it because he thinks it's encapsulated in a rock. He sees this bony structure and he says, well, that's the end of a bone sticking up, and if I could get everything away, I could bring this bone out of here because it's all covered with rock. Well, I'm going to just play this and speak about it because the guy did a fabulous job. I was impressed. He understands chemistry, you know. Anyway, here goes. So he says it's encased in a rock, but it's a bone. He believes the fossil is 80 million years old, so he decides to uncover it. He wants to get it out of that bone. Well, if you've been following me, you understand that the bone is just part of the flesh of the body of the creature. Now, he's taken the body of something and he's removing the flesh, just like you remove the flesh from this goose head, and the feathers, and the eyeball, and the beak, and you'd get down to the bone that's inside, which you can see the structure of the neck inside here if you look at it really carefully. Now, he's going to do this with chemistry. Look at this. This is very cool. You put the fossil in the vinegar for 1 hour, and it softens it up. It's an acid. It's important that the fossil is only left in the vinegar for 1 hour and that the water is changed every 3 hours. I don't know how it can be only left in there for an hour and changed every 3 hours, but that's fine. Now, he keeps chiseling away. Now, the vinegar must be seeped away before he applies. I'm not sure exactly what he is doing here, but he's using different types of chemistry to eat away at the surface, and then it's something he just put in there stabilizes the calcium type matter, apparently. And now he's removing the fleshy type matter that encapsulated the bones. I mean, it's just the way it is. Now, the reason this is cool is because he found out what kind of a bone this was. I would look at it and just say, well, it's a bone of some kind of creature. You'd have to do DNA on it. But he did this and then matched up what this bone structure was to a, well, yeah, I'll just keep playing. Here it goes. So he keeps chiseling away all this stuff, and because he's done the right kind of chemistry, he's turned some of the stuff weak and some of the stuff tough. And they're two different stuff, and I can show you that on my bones here too. Before I go any further, let me just show you what this one is. This is a human fingertip, and I know it for a fact because it's been DNA certified. The whole hand basically came out of the same spot, and this is just part of it. Now, that's the bone. This is all the fleshy stuff that was attached to the bone. And you can say, well, Roger, how can you say that? That's just something laying on there. That's just sediment. No, it is not, because the other side of the bone has the muscle still on it. That muscle is still wrapping that bone. You see the bone ball here? This side still has the muscle wrapped on it. That's the weave of the muscle. That is literally a tendon. And I've always told you that they break off at a spot, a flat spot right here. Snap. That's the abrupt transition. That tendon went back to this tendon mat that ran all the way out to the fingertip. And the fingertip, at the very other end, you know, it's another few feet out, is fingertips like this. All right, and that's a fingertip. And again, this is from the same hand. I'll show you the palm. Now, if I chipped away, this looks like mud. It just looks like a dirty, muddy rock. Well, these are the pads on the bottom of your finger. Exactly the same. That's where the apical tuft is, which is where all these little balls hold on to the little tendon straps that come back so your fingers can do all these things. They run with tendons. Now, I broke the edge off here. You can see it's not mud everywhere. It looks like mud, but once you get inside, the flesh has a different texture to it. And once you get deep inside, the bone here, which is this bone right here, and I have a CAT scan of this. All right, so I know where the bone is, and the bone is right here. This is a little bit different than what you're going to see as the flesh. And so if I did the same stuff he's doing, which I never would do, but if I did, I could get down to the bone. I have bones coming out of the ground as bones themselves. They've already defleshed themselves. And that is, there's certain conditions that cause certain deteriorations. And this was a bone, and blood came out of this bone. And I can prove it was blood because they'd say, oh, it's just iron oxide. Well, let me show you what iron oxide does. And iron oxide does not create clotting factor. All right, this is a bone. I can't remember whether this one or not, but it's a bone. And it was, and that's the blood coming out of one of these bone foramen, which is a little, they have blood vessels coming out. Well, I'll show it to you. And underneath the scab, which is a scab, you say, oh, that's just ferrous oxide, that's just, no, it's not. Because ferrous oxides do not come along with clotting factor called fibrin. Just look it up, it's fibrin. And plus, this has the blood vessels right below it, and I will show you those as well. So we have the blood, which this is raw blood. I mean, it's literally raw blood. The stuff I sent in for testing for DNA on my stuff, they said was excellent quality DNA, basically like right out of your arm. That's the clotting factor. Below that is the blood vessels. Obviously, if they have to be there, if the blood is leaking out of there, and here they are. All right, you see that one right there? That's the red blood side. See, that's the red blood side. That's the artery side. What's the difference between an artery and a vein, which the vein is here? The artery has red blood, which has an extra oxygen. And that's why I kind of like this guy's work, because he's doing some chemistry, and he understands that you can, well, maybe he doesn't understand. I don't know what he understands. Let's put it this way. He obviously understands the bones, how to get to that bone, and how to preserve that bone and still make the rest of the stuff etchable away. But anyway, you don't have to do that. These bones have these same little holes all over. And then that's the marrow in the bottom. That's the marrow. This actually does have a piece of bone left. You're never going to see it. You got to get the microscope out. It's right there. Well, maybe you will see it. Hold on. You see that? That's the bone that's left. But nucleophilic substitution will continuously invade something. And that's why this stuff about carbon dating and all that, it's insanity. These things are in wet, moist conditions. There's a continuous invasion and changing of the molecules that exist within everything that's organic. Because everything that was organic was unstable. And the only reason it became stable was because it was in this aqueous solutions that invaded it. And it's called nucleophilic substitution, nucleophilic invasion. Just look it up. I'm showing evidence here that you just can't deny. And it's being denied because of the ancient thoughts on, forget about this, we're the geologists, experts, and you do what we tell you to do, and then you're going to know the names of all these rocks. Well, good, the names are wonderful. But I can tell you one thing, all kinds of stuff. This is flesh. That is flesh from I don't know what it's actually from, but it's flesh, and that's all the loose connective tissue inside of it. When I first came out of the ground, it looked just like a piece of meat. And, well, let me show you something. You see that? That's when it first came out of the ground, this rock right here. It's getting dried up now. But they oxidize after they're out of the ground and they're not entombed in the muddy conditions anymore. That is what's called fascia, interstitial, it's tendinous, the tough stuff you don't want to eat when you have your steak. You want that nice red, look at that marbly effect. Oof, oof. Anyway, that's what it looks like in your body is this, right here. That's that flap. That's that flap. I just showed you that flap that hangs over. That's the interstitium, which means that this organ or whatever it was gets locked in to the other part of your body. This, I believe, was a lung, and that's the interstitium that comes out and snaps it in to. Well, I have a lung here. Hold on. All right, this is a lung, and this has been DNA tested, human lung, and this is where that flap is on the bottom, and it lays down and attaches somewhere down the bottom here to hold your lung in position, so your lung can move it around a bit. But I call them the interstitial latch, and they all have them. And there was one at the top too. It's broken off here. But your organs have to stay in place. They can't just drift around and go upside down and everything. So that's that flap, and it attaches to muscles. It attaches to organs. And again, here's the rock that I had, and that's that flap. You see it right there? That's that latch, and there's a different chemistry right at the spot where it locks in. And I've studied the chemistry pretty deeply on these things, and I suppose we go a little further with this, but they just can't come to grips with the fact that biology can very, very easily turn into stone. All biology, not just creatures with flesh and blood, but trees and plants and everything. Those can turn into rocks too. I'll show you some trees that have turned into rocks, absolutely fabulous looking trees, because if they're in certain conditions. Now the trees did not hold up well in the salt waters, and I believe this was a great saltwater flood that created these conditions, which really preserved well tissues of flesh and so forth. Okay, these are tree sections, and nobody cut them like that. They break like that because trees have different segments. They're like cellular construction, where in addition to membranes, we only have membranes. They have cell walls, then they have membranes. It's a little different, and they create these little chunks, like somebody cut them, but they weren't cut. Now, this is, there was an area here, something died here that had a ton of blood, and that is the blood there must have been some salts or acids or whatever, and it invaded these trees with transition metals. I'll show you a little more. All right, here's another one, a tree that was invaded by transition metals. Now, trees normally don't get invaded by transition metals unless they died where something was really bloody. That's my take. Because normally salts would destroy these, they would deteriorate. Just like that guy showing how he chiseled the stuff away. Don't use the vinegar for too long, don't do this, don't do that. Well, the same thing with trees in salt waters. They just don't do well. They get the membranes and the cell walls break down. All right, this does get a little deep, but it's not hard to understand. You have to just understand the transition metals. And it's called nucleophilic substitution. And all they do is they look at them in the laboratory. But now they're going to look at them and understand what's going on in the biology, because that's where enzymes are and catalysts. And those are things created by bacteria. I'm not sure they understand all of the biomolecules, but this is the first time that we'll be seeing real biological organic reaction mechanisms. Then they say don't be intimidated, it's the complexity and they're big molecules. Well, the reason they're big molecules and complexity, these are the things that keep you alive. And what they do is biological nucleophilic substitution is how you stay alive. Not a single molecule in your body, not a single one, except maybe the enamel on your teeth, is stable. Not a single molecule is stable. It would just rot away right in literally a day or so if it did not have the correct nutrients brought in and the correct nastiness brought back out. That's how every molecule in your body stays alive. It has to transpire or respirate. It has to give up stuff and take stuff in. It takes in oxygen, it takes in nutrients and glucose and all that nonsense. And it gives up all of the nasty stuff, all this acids and salts and things that are going to damage tissues. And that's a process done literally by bacteria. They create the enzymes and the catalysts that they're just talking about here, the roles of the enzymes and the catalysts. So this is the first time they're really looking at it in this, this guy is looking at it, or whoever's looking at it here, the first time they're looking at it, as a biological mechanism rather than using it in the laboratory to create chemicals, because that's what they always did. They create biochemicals in the laboratory using these nucleophilic substitutions. Your body does the same thing, only your body does it elegantly using bacteria. And bacteria, they can't do anywhere near what bacteria can do in the lab. Impossible. Bacteria is so much more advanced. And I'm not kidding you. I'm not joking about this. Bacteria is absolutely amazing. And there are bazillions of strains of them, and every one of them has a job. And they live in biological systems, basically in your membranes. They live in the watery substances in the membrane that separates nastiness from good stuff. They create mucus to keep all that nasty stuff out. They create serosa. They create all kinds of biology and enzymes and catalysts, and that's your protective mechanism. That is your innate immune system. Listen to me. Membranes, they protect you. They're walls, they're barriers. They're constructed of membrane tissues with little holes in them all over the place, a bazillion holes. And what lives in those holes? Bacteria. They live in fluids in those holes. And now they realized this just recently, and now they're calling it the new organ system. It's called interstitium. And it's only been recognized this way for the last few years, that it is so important to your whole body, because all this stuff flows through your body. These probiotics, basically, they're bacteria that work for you, not against you. And this is a new revelation in medicine, in biology, and everything, is this nucleophilic substitution and how biology of bacteria does this in your body. And that's the bacteria. You don't have the bacteria, it's not going to happen. And you're going to be sick. You're going to have Crohn's disease and digestive issues and bowel problems and fistulas and colonoscopy, colon issues, and your stomach. You're going to be sick. You're throwing up. It's a system. You don't take care of it, and you don't have the right products in there, which is the bacteria. You're gonna be sick. So that's just an offshoot of looking into rocks, because the rocks. This guy that was chiseling away at the rock and giving it vinegar and so forth, he was reversing the process of stabilization. And it's a reversible process. You give, you take. That's how these nucleophilics, well, they call it the leaving group. Well, here it is right here. All right, this is the first time you're going to be seeing real biological or organic reaction mechanisms. Do not be intimidated by the size and complexity of the reacting biomolecules, as they are enormous. They are just organic molecules. Exactly. They're made organically in the creature's body. They have the same bonding patterns and functional groups that you are already familiar with. Focus on the reacting parts of the molecule. What is a nucleophile? What is the electrophile? What is the leaving group? In most biological organic reactions, the main bulk of the biomolecule is just going along for the ride. Those are called the transition molecule complexes, and they have ligands on them. That's the molecule that's just going around for the ride. Well, it's grabbing onto this and dropping it off and picking this up and dropping it off. They can often be abbreviated with the R group to simplify the picture. That's the main group, and I'm going to show you that in transition metals in a second, because that accounts for all these colors you see in rocks and opals and everything. And it's all conditions, it's all based on the conditions of the waters that these things were in, what their chemistry was, and was it next to a kidney, was it next to bile, was it next to acids, the stomach, was it in the digestive area, because their organic molecules do the invasion. And I'll show you what I'm talking about, transition metals. Okay, just one more little bit about it. Nucleophilic substitution with the silicon. Silicon and carbon are right on the same row in the same group in the periodic table. So they have a very similar behavior in the body, and that's why we see a lot of silicon here and there in fossils. All right, now I'm not saying that every single thing there is not a concretion, because there are things that do concrete. Yes, absolutely. Because, say again, it's chemistry. It's what will attach to this if it was all by itself as a bone. Well, there's a lot of calcium, so it's going to look for something that might have a lot of the other side of the periodic chart, because the calcium's way to the left. It would want to bond with something on the other side. It may take on who knows what, but it's got to be in the right moisture and compacted in the right stuff to be able to be invaded. And if it still has its flesh on it, it's going to end up like what he did. He took the flesh off to get to the bone, and but he did discover and identify what it was. It appears that he's identified what that thing is. He's got it down to a pretty good, right to where the bone is. But again, you don't have to get to the bone. The bone is covered with the flesh. If you look for the flesh first, and this one did it all by itself. It uncovered its bone. And here's where the bone capsule is. You see that? That's the capsule of the bone. Inside here is the marrow and all that stuff. Now he would chisel down and take all of this stuff away, chisel, and he'd get down to where this is, and he would go around it and he'd say, whoops, I got a bone. Well, yes, you do. But if you looked at the other side of this bone ball over here, instead of the bone, you have the flesh. And the flesh is, to me, better than the bone. I go for the flesh instead of the bone. Now, that right there is a tendon. That's the abrupt transition. You see that little round spot there? That's what fed this muscle that was attached to this, that came up to the fingers, and they moved the fingers around. I'm going to show you the anatomical, but that is the little tendon, and they go between the fleshy part and then the next muscly part. And of course they attach with something similar to it. And he'd do the same thing. He'd chisel all this stuff away until he hit something like this. Well, he wouldn't. He'd chisel that away until he got to the bone, and then he would end up here. Because this had the same thing over here. It had one over here, the same stuff. In between your fingers you have tendons that run out, one side and the other. You have a big flat strap of tendon, which I will show you. And this is obviously extremely eroded. And it was in a very, very wet, invasive area. But you can still see that's blood. And I have a lot of this one. I have the hand, and I have fingers, and I have other stuff from it. And it's a pretty good size. This is a fingertip. And I believe this is a thumb, because the thumbs have the bones offset instead of right in the center. And because you take your own thumb, and pinch it, and you're going to find one side you can go in, the other side's flat. This side you can go in, you see it? And the other one's the same way. You got one side that goes up pretty much straight, and the other side has that big lump hanging off at the side. Same thing with this. So the bone is on one side, and I broke that off. I think I showed you before. But anyway, and this had the apical tuft. You see that round spot right there? See if you can make that out, that round spot. That's where the apical tuft sits in between the end of the finger. And we have the biggest apical tuft of any creature on the planet, bigger than a gorilla. And that's where the apical tuft is here. And I have one here somewhere. I don't know what happened to it, but it's around here somewhere. That is, it's eroded all the way down. Oh, here it is. Hold on. This is what happens at the apical tuft. You see these big holes here? You see that ball? That's what sits here. And then there's a whole bunch of little straps come up, and then they attach at the end with balls. And I'm going to show you this in the anatomical. It's quite obvious. And this was the apical tuft. And I believe it was from this same hand. It came out of that same hole. And stuff was very, very eroded, and some other stuff was not eroded at all. It was perfect. It must have been sitting like sideways-ish. And because because even that, one side is totally eroded, and the other side's not too bad at all. So this is the kind of stuff I don't know why exactly. There's a lot of research to do on this to understand what we're seeing and how it all happened. All right, let's just start with this little piece right here that's broken off. I said was this. You see that? It broke right off there, and there's a little round spot on the end here where it attached to the muscle. The muscle bundles run out of it. Now this is from the other side. All right, but there's one on this side, there's one on the other side. So there's one here, and there would have been one over here. This one is the eroded part, and now we can see the bone ball, which is underneath. This flat strap is that flat strap right there. All right, the bone, if you could look, I got a lot of shots of this. But the bone itself that we're talking about is this bone right here. All right, that's the bone ball right there. And these muscles wrap around that bone ball. You see it? The muscles wrapping around. And that's what we see here. That's the muscles wrapping around the bone ball. And that is that little tendon spot that comes down I showed you before. It doesn't show it in this shot, but that's the tendon. Can you see? Oh, there you go. That's the tendon that runs off the side. And it broke right there. That's this tendon right here. So there's your muscle fibers. There's your tendon broke off. That's where the little attachment to the muscle fibers is, that round ball there. Well, not a ball. It comes out and attaches. There's an abrupt transition. You see how this white right here? And bam, it stops right there. That's an abrupt transition from tendon attached to muscle. They're all over your body, everywhere. Your body is loaded with tendons and muscles. Now, remember I showed you the apical tuft? All right, you see it up there? The very tip is what's called the apical tuft. And that was this right here. All right. Now, that ball right there is a little tendon ball. And those little tendon balls run, you see down here? I'm going to show you where the tendon balls run to. Now, you got to look close. You see those fibers? Let me see if I can home this in. Let's see. I hope this is visible. But anyway, there's a bunch of tiny little fibers here, and they attach to the apical tuft, which is right there. And one of those balls is still attached. Every one of them had a hole that they attached to. And then the straps, of course, broke off, and this broke off the tip. Now, our fingers are bigger apical tuft than a gorilla. All right, this is the gorilla compared to the human hand. Now what I want you to look at is right here. That profile right there at the very tip of that fingertip. All right, that's what's called the distal phalanges. And I think before I called the apical tuft the distal phalanges, but let me see if I can find the bone. Oh, I can never find anything when I need to find it. Well, I have a bone here that has this exact same pattern in it, which is, let me find it and then we'll see. Okay, my friends, this is that fingertip. This is this fingertip right here that I showed you. You can actually see the fingernail pattern in here, and you can see the tendons very well. I broke this one off just to see what was inside there, and it's a totally different material because it's flesh compared to the outside flesh, which is grip skin and so forth. Now, this is the CAT scans. And again, these are the tendons right here. There's two extremely heavy-duty tendons. And you see this is a dark and this one's white looking. Well, why is that? Well, it's because of the way your blood is fed up to your hands. You know, one side has the dark blood on it and one side has the red blood on it. That's the difference. That's why we're seeing two, but you can see pretty clearly. Now, this is the bone pad. And the bone is offset, so I'm almost sure it's a thumb. You see how your bone is offset on a thumb? Now, I'm just going to play it. This goes back 6 years ago. And I had 3 DNA tests done. I had these CAT scans. I had all the specimens, and not a single, and up to today, not a single institution will discuss this, not one, because these are giants. This is a giant human being, and it is proven to be human, and anybody can test it right now, and it's human blood, and there's plenty of blood to go around. I showed you. I can get right to the veins, right to the arteries. No problem whatsoever. Now, what did I say back then? Let's see. It's the body. I believe they call it the proximal end, and the other end is the furthest away from the body, the tip. Now, I believe this is the bone. I have an anatomical specialist who's going to be looking at this, a structural guy that does autopsies and very, very, very good at this stuff. Yeah, it confirmed 100% of everything that I've said. Every claim I've made has not been dismissed by anybody. Very few people will stand up and say, yep, he's right, but nobody will stand up and say, nope, he's wrong. The only do they come up and say, nope, he's wrong, and then just walk away. There's no evidence to support that I am wrong whatsoever. I have evidence, overwhelming evidence, scientific evidence that you would expect would be at least examined by the people that are teaching our kids, and they are the ones that are closing the door on truth. You'll know better. All right, these shots show the areolar tissue. All right, I'm going to be talking about some in-depth stuff, but that's the bone right there. You see it's offset. You can see it fairly well if you look carefully. And if that guy chiseled down through here, he would eventually get to that bone. And there's the outside layer of the bone, there's the inside layer of the bone. And that's going down, that's this right here, going down this way. And of course, these are the blood vessels that go around, and then they scanned up through the whole thing. You can't see a lot in these because they have transitioned. That's why it's almost hard to see the bone. And that's why people have never understood this before. But it went right up through here. Oh, here's the one shot. Hold on, let me get back here. This is a shot that shows it right there. Stain here, the ferrous bone stain, and it has an apical tuft which is in this bone. You can see this. You see the outline of the bone. Yeah, you see the outline of the bone. That's the bone you would see if he chiseled down and got to the bone. Now, that's that black pattern that I showed you of the distal phalanges, right, the tip of the fingertip. And of course, there would be an apical tuft on it. What else did I? Oh yeah, this is the hand. Let me see. This was, like I said, 6 years ago, and I was I thought I did a pretty good job of presenting it. And let's see what I showed for the hand, because the hand is also a part of this whole thing that's been DNA certified. Here goes. Emplacements on the side, and that's how the flesh invests itself into the fingertip. Or tendons, actually. It's going to be kind of hard to see, but literally this is a different kind of tissue than this down here. That's like in the palm of the hand. This is like the deep flesh of the hand. And this is what he'd be chiseling away to get to the bones. The bones are in there. Their bones are absolutely no question whatsoever. They're in there. But they're in there just as I showed you that other matrix that has eroded half of it off in half. This is going to be coated with muscle. They're going to be coated with tendon. They're going to be coated with it. And he's going to chisel all that stuff away. And he's going to end up with bones. Yeah, you could do that. Spend the rest of your life doing that. I'd rather see the whole thing in its entirety. And this silver part is the grip skin. You see this? It's peeling away. The reason it's peeling away is that skin is way tougher than the average skin on your body. Way tougher, extremely keratinized. I've studied this very, very well, and I understand exactly what's going on here. And again, he'd chisel down through this tendon, this layer, and through this fleshy layer, and he'd get down to where there's bones, and then everybody'd say, "Ooh, this is fabulous." But they'd never do it and say it was a human being, trust me. And I did it, and I proved it was a human being. I have the CAT scans, I have the DNA, I have the anatomists, I have the chemistry. The process is now fully understood, nucleophilic substitution. It's time to confront reality.